Hi there. Today we are tackling Calculus Section 3.4. We'll learn how to describe motion by looking at position, velocity, and acceleration. Think of these as the story of how an object moves. Welcome to the heart of kinematics. To understand motion, we need to master the golden trio: position, velocity, and acceleration. Position, or st, tells us exactly where our object is at any time. Velocity, v of t, is the derivative of position. It tells us how the position is changing. And acceleration, at, is the derivative of velocity. It measures how quickly that speed is changing. Remember, it's just a simple chain. Differentiate position to get velocity, and differentiate velocity to get acceleration. That's all you need to start. To figure out if a particle is speeding up or slowing down, we look at the signs of velocity and acceleration. If they have the same sign, both positive or both negative, the object is speeding up. If the signs are opposite, they are working against each other, meaning the object is slowing down. Remember, it is all about whether they are pulling in the same direction or fighting each other. Let's look at a classic polynomial motion problem. We are given the position function s of t equals 2t cubed minus 3t squared minus 12t plus 8. To find the velocity, we take the derivative of the position function. Using the power rule, we get 6t squared minus 6t minus 12. Now, for acceleration, we derive the velocity function. That gives us 12t minus 6. This tells us exactly how our object's speed is changing. These two functions are our tools. By comparing the signs of velocity and acceleration, we can determine exactly when the particle is speeding up or slowing down. To understand how a particle moves, we start by finding when the velocity is zero. This tells us where the particle stops and changes direction. For our function, we find that the velocity is zero at t equals 2 and t equals negative 1. Now we look at the signs of velocity and acceleration. When they have the same sign, they work together to speed up the particle. When they have opposite signs, they fight against each other, slowing the particle down. Notice how, when both signs are the same, the particle speeds up. This simple sign analysis is the secret to unlocking the story of the particle's journey. Keep this in mind. Same signs always mean speeding up, while opposite signs mean slowing down. It is that simple. Let's look at exercise 151. We are given the position function s of t equals 2t cubed minus 15t squared plus 36t minus 10. To find the velocity, we apply the power rule to each term. Differentiating each term, we get 6t squared minus 30t plus 36. This is our velocity function. To see where the particle stops, we set velocity to 0 and factor. Factoring is incredibly helpful because it clearly shows the particle is stationary at t equals 2 and t equals 3 seconds. Sometimes our position function is a fraction, like s of t equals t divided by 1 plus t squared. When we see t in both the top and the bottom, we use the quotient rule. A great way to remember the quotient rule is low d high minus high d low over low low. Low is the denominator and high is the numerator. Applying this, we take the derivative of the top, which is 1 times the bottom, minus the top times the derivative of the bottom, which is 2t. All of that sits over the denominator squared. Now we just simplify. Combine those t squared terms in the numerator to get 1 minus t squared. This gives us the velocity for this complex rational motion. The big takeaway is to reach for the quotient rule whenever your function looks like a fraction. It handles those tricky rates of change perfectly. Let's look at a rocket launch. The position of our rocket is modeled by the function s of t equals negative 16t squared plus 560t. To find the velocity, we take the derivative of our position function. Using the power rule, we get v of t equals negative 32t plus 560. Now, let's find the velocity exactly 3 seconds after launch. Plugging 3 in for t gives us negative 96 plus 560, which equals 464 feet per second. Finally, acceleration is the derivative of velocity. Since our velocity function is linear, the acceleration is constant at negative 32 feet per second squared. This is the constant pull of Earth's gravity. Let's analyze a car reversing. Its position is modeled by the function s of t equals t squared minus 3t minus 4. First, we find the velocity by taking the derivative. This gives us v of t equals 2t minus 3. Next, we find when the car hits the garage door by setting position to 0. Factoring gives us t equals 4 seconds. Finally, plug t equals 4 into our velocity function. We get 5 units per second. This is how fast the car is moving at the moment of impact. Let's look at the path of a hummingbird. Its position over time is given by the function s of t equals 3t cubed minus 7t. To find the velocity, we just take the derivative of the position function. Applying the power rule, we get 9t squared minus 7. Plugging in t equals 1, we find that the hummingbird is moving at 2 meters per second. Acceleration is the rate of change of velocity. Differentiating 9t squared minus 7 gives us 18t. It is that simple to track motion. Remember, position leads to velocity, and velocity leads to acceleration. Just keep differentiating. Let's look at a classic potato gun problem. We are given the position function, s of t equals negative 16t squared plus 100t plus 85. To find how fast the potato is moving, we find the derivative to get velocity, v of t equals negative 32t plus 100. To find the speed at 2 seconds, simply plug 2 into our velocity equation. Negative 32 times 2 is negative 64. Adding 100 gives us 36 feet per second. This tells us the potato is still moving upward at 36 feet per second. Remember, velocity is simply the rate of change of position. Once you have the derivative, you can find the velocity at any moment in the potato's flight. To find the maximum height, we just need to find when the potato stops moving upward. Since velocity is the rate of change of position, we set the velocity to 0, solve for time, and plug that time into our position function. To find out when an object hits the ground, we set its position function to 0. This gives us a quadratic equation. Negative 16t squared plus 100t plus 85 equals 0. We use the quadratic formula where a is negative 16, b is 100, and c is 85. Plugging these values in is the most reliable way to solve for t. When we substitute our numbers, we get 2 possible values for t after calculating the discriminant. We get roughly negative 0.74 and positive 6.99. Since time cannot be negative in this context, we discard the negative root. The object hits the ground after approximately 6.99 seconds. Always remember to check which solutions make sense for your physical problem. Determining where a train is headed is straightforward. It all comes down to the sign of its velocity at any given time. If velocity is positive, the train moves east. If velocity is negative, the train moves west. Let's look at an example. If the velocity is v of t equals t minus 4, what happens at t equals 1 hour? Since the result is negative, the train is moving west at that moment. The quickest way to check is simply plugging your time value into the velocity function. A simple sign check tells you everything. To understand how a particle moves, we use a simple visual tool called a sign chart. We stack 2 number lines, one for velocity and one for acceleration. By looking at the intervals where they are positive or negative, we can easily spot the behavior. The rule is friendly and simple. If they have the same sign, the particle is speeding up. If they differ, it is slowing down. This chart keeps your signs organized and prevents common mistakes. Give it a try on your next problem. When you see a position function containing a negative 16t squared, it means Earth's gravity is already baked into the equation. Let's see why this constant is so important. By taking the first derivative, we get the velocity function. The power rule turns the negative 16t squared into negative 32t. Now we take the derivative again to find acceleration. The derivative of negative 32t is just negative 32. This is Earth's constant gravity in feet per second squared. Regardless of the initial velocity or starting height, the acceleration due to gravity on Earth is always negative 32 feet per second squared in these physics problems. Think of velocity as a vector that tracks where you are going. If velocity is negative 5 meters per second, it just means you're moving backwards. Speed, however, is simply how fast you are moving. To turn velocity into speed, just take the absolute value. Here's a pro tip. Don't let a negative sign confuse you. In kinematics, a negative velocity simply means direction. It doesn't mean you are slow. Always remember that speed is the magnitude of that velocity. When you are stuck on a kinematics problem, tools like Desmos are your best friend. Let's look at a simple position curve. S of t equals t squared. Notice the slope of the tangent line? That slope is exactly your velocity at any given time. As the dot moves, the steepness changes, showing you the velocity directly. To master kinematics, remember our chain of command. Position is the start. When we take the first derivative, we get velocity. Take the derivative again, and we land on acceleration. Next, always check your signs. If velocity and acceleration have the same sign, you are speeding up. If they have opposite signs, you are slowing down. You now have all the tools to solve any kinematics problem. Keep practicing these derivatives, and you will do great. Congratulations! You have navigated the world of kinematics. Let's look back at the core tools you've mastered for solving these problems. Remember, velocity is simply the derivative of your position. Acceleration follows as the derivative of velocity. Always check your signs to know if you're speeding up or slowing down. And whenever you need a turning point, set your velocity to 0. You now have the tools to solve any kinematics challenge. Practice these steps and you'll master Calculus 3.4. Keep moving forward.